So when we go to a lab, when we go nature, we find different type of matters. We don't know what it is. So empirical formulas and molecular formulas help us determine the structure or the composition of that type of matter. So if we find a powder, we can say, okay, that powder is aspirin because it contains carbon, hydrogen, and oxygen in a very specific ratio. Don't forget, compounds have very specific ratios. If I find something with a different ratio, it's no longer that type of matter. So if I find that it has 10 carbons instead of 9, that's no longer aspirin. It is something else. And we do that so we can go from the microscopic to the microscopic world, and we still use that mole concept. So the idea, how do we bridge that gap between 10 grams of white powder to something that looks like C9H8O4, that is aspirin? How do we determine the identity of that powder? And we are going to follow a set of steps. We're going to follow a process that's going to allow us to do that. In order for us to be able to follow that process, we had to define this calculation that is called percent composition, which is done the same way you do in math class. It's just part over whole times 100. In this case, it's more applied to elements. So the percent of the element in a compound is the mass of that element divided by the total mass of that compound times 100. We did a little bit of this already in class. So if I have, let's say, 10 grams of a sample, and I have 2.5 grams of hydrogen versus 7.5 grams of carbon, I can calculate what percent of hydrogen and carbon I have in that sample. And that's going to be crucial and important for us to identify what that substance is. And because compounds have specific ratios, the percent of each one of those elements in that compound will also be fixed. So if you change the percentage, you are changing what that substance is. So let's make sure we keep that in mind as we're working through these problems. Okay, so we take that white powder, we do an analysis, and we obtain the masses of all the elements present in that powder. From those masses, I can do analysis and calculate the percent of each one of those elements in that powder, which is going to give us a profile that says, okay, this powder has 61% carbon, 15% hydrogen, 23% nitrogen. So now I know how much of each one of those is in that material I have present. Percentages translate to masses. So if I assume 100 grams of a substance and I know the masses, we can calculate that percent. Well, let me rewind. The mass of each element is calculated based on the masses of each one divided by the total mass times 100. That's the percent by mass that I was referring to in this case for aspirin. So now we know that I can take the sample, I can do an analysis in a lab, calculate the mass of each one of those elements present, and from those masses, I can calculate the percent composition of those elements in the sample. Those percentages are going to give us what we call the empirical formula. So it's the pattern, is the structure that relates all the elements in the sample that I have present. So let's say I have CH2. That's the pattern that I'm looking for. The molecular formula is going to be how many of those small patterns I can see in the big one. This one is a little misleading because it has 3, 6, 9, so it should be 9 times the 18 hydrogens. It forgot to add 3 more units in there, but molecular is made of the smaller pieces. So it's the empirical is the smallest ratio between the elements in that substance. The molecular formula is a factor of that small ratio. So the molecular formula in this case will be made of 9 times the small one because I can see the small one repeated 9 times in here. So the mass of the molecular will be 9 times the mass of the empirical. Again, the empirical is the smallest simple ratio of atoms in a compound. It has to be the smallest ratio. So if you get C4H8, you have to simplify that. If the ratios can be simplified, it's not an empirical formula. It's most likely a molecular formula. The empirical formula cannot be simplified any further. And I repeated that like 3 times already. So try to get it embedded in your head so you don't forget, because you will have question, which one of the following is an empirical formula? You're looking for the one where you cannot simplify the ratios anymore. And you don't need to know what the name or the identity of that substance is. You're just looking at the ratios. So now that we know that we can have empirical formulas and molecular formulas, how do we go about calculating empirical formulas? We are going to follow this process. You are going to be given a percent or a mass. That mass we have to convert to moles because we cannot do anything in grams. Remember, moles is your base unit for all the calculations we are doing here. Once you have the moles, I am going to divide by the smallest mole value. That's going to give us a ratio between all the elements. That ratio is going to be translated into an empirical formula with the sticky note that I have in here that says that that ratio has to be a whole number. If I do not have a whole number, I have to make it a whole number. And I'll show you how to get those whole numbers in a second. Okay, so it's a like 1, 2, 3 step process. It sounds like it's a lot of work. It's not really. So let's look at this sample in here. I have iron and I have oxygen. I have 34.97 grams of iron. I have 15 grams of oxygen. The first step is converting to moles. So I divide by the molar mass of iron, divide by the molar mass of oxygen. I get the number of moles. Then I divide each one of those moles that I have in here by the smallest one. So by looking at them, the smallest one is 0.6261. So I divide both by that. If I divide 0.6261 by 0.6261, that gives me 1. That's for iron. And if I take the 0.9394 divided by 0.6261, it's going to be around 1.5. I told you, you need whole numbers. 1.5 is not a whole number. And please don't round. So to convert that 1.5 to a whole number, I can multiply the 1.5 times 2 because it will give me 3. I mean, you You multiply by 2 to get 3. But if you multiply the oxygen by 2, you have to do the same thing for the iron. You cannot do it for one and not the other one. If you do that, instead of having one iron, you're going to end up with 2 irons, and the 1.5 multiplied by 2 is going to give you 3, so 3 oxygens. Those are the whole numbers that become subscripts, giving you the structural formula or empirical formula for these two elements combined together. Again, you are given grams, convert to moles using the molar mass, then divide by the smallest ratio. Check to make sure you have a whole number. If you do, you just write the structural formula and put those subscripts in there. If you don't have whole numbers, you multiply by a factor that's going to give you whole numbers. In this case, that factor is 2. And you have to do it to all the elements. You cannot do it just to one. So if you do it to one, you have to do it to the other one. And that's how you ended up with F iron oxide. And it's iron 3 oxide, because the charge of that iron in here will be plus 3. Okay, I think I have another example. Now I'm given percentages instead of grams. Same thing. Because if you assume a 100-gram sample, the percentage is how many grams you have. You don't have to do anything else. Because when you multiply that percentage times 100, it's going to give you the same mass. So 27.29% of carbon is the same as 27.29 grams. Take the grams, divide by the molar mass to get the number of moles. And I do the same for carbon and oxygen. That gives me, and when you look at the numbers, you divide by the smallest one. You divide the first carbon by that number, it's going to give you 1. When you divide the oxygen by the moles of carbon, it's going to give you a very, very close to 2. In that case, you can round because it's extremely close. You don't have to find a factor. So 1 for carbon, only 1 carbon, 2 for oxygen, 2 oxygen. So these percentages are the percentages for carbon dioxide. Okay. Let me see what's coming next, so just get an idea. I'll come back to this. Okay. We are going to summarize a couple of things in the next slides, and then I'll do an example for you. Okay. So when you don't have a subscript that's a whole number, if it ends in 0.5, you're going to multiply by 2 to get that whole number. If it is between 0.33 and 0.66, you're going to multiply by 3. If you're going to end in 0.25 to 0.75, you're going to multiply by 4. So you get just those whole numbers. This is just a guideline. That doesn't mean that it's always going to be like that. So most of the time, those subscripts are whole numbers. Write out the calculation so you don't have to worry too much about what factor do I have to multiply by. But if you have to, this is how you do it. And I usually don't tell you what the factors are. I just decided to do it this time around just to help you out. Okay. So that's how you do empirical formulas. But then I also have this thing called molecular formulas. And molecular formulas, I told you, is how many units of the empirical I have. So it's empirical formula times the factor n. So the molecular structure in here has 180 AMUs, but the empirical formula is 30. So if I take 180 divided by 30, it's going to give me that n factor. So in this case, it's 6. So 6 times 30 is 180. And what happens is you go to a lab and you know the amounts of each of the elements, and you get a molar mass for that substance. But by doing the empirical calculation, you get a different mass that's much slower. When that happens, oh yeah, because the mass I got from the sample is a molar mass, is a molecular mass, is not the empirical mass. So you have to do a different set of calculations to determine what that molecular mass is. And I'm going to do an example that incorporates all this pretty soon. Just to finish this, so the factor N is the molar mass divided by the molecular empirical formula mass. How many times that empirical mass fits into that total mass that I have? And it's molar mass, so you don't confuse it to grams mass. So you're going to have to calculate the empirical formula mass. The molar mass of the substance is most likely going to be given to you. So you can divide that molar mass by the empirical mass, giving you the N factor. And you need the N factor because you need to calculate the formula of the molecular substance, because it's no longer going to be an empirical formula. It is going to be a molecular formula. And it seems complicated, but it really is not. Okay, we did this already, so I'm going over that one. So let's do an example because that's the only